Number 4, the digital twins. Yeah, so this means using a model. So we actually use the same model as we use maybe in the virtual piloting, virtual process design. Now we recycle, let's say, the model, transform it a little bit in a fast version to be used in the operational stage for smart operation. So this is the topic of digital twins. And yeah, I think, I know, I will shortly introduce this and then I will give the word to my colleague. So what is a digital twin of an ozonation process? To our understanding, how we define it typically is it's a bunch of mathematical equations. We don't care how they look like, but it's some magic, let's say, in mathematics that gives you variables or insights you cannot measure based on what you can measure. For example, when you look at ozonation, just imagine you would have a digital twin that predicts in real time your bromate, the removal of your target contaminants, for example, a set of 10 or 11 or 5 chemicals of interest. That would be of value because you cannot measure them in real time, but the operation depends on it. So this is really smart and proactive operation. But on top of that, you can also use the model offline for additional what-if testing. Now, what we also saw is that it leads to accelerated training in terms of a flight simulator. So we literally have customers that start playing with the model themselves to really accelerate the learning and the process understanding. Yeah, so you have actually a flight simulator at your disposal. So Giacomo, now you can elaborate a bit more on this topic.
There we go. Thank you. And what you see here is the conceptual workflow that brings from a very highly detailed CFD plus kinetic simulations toward a dynamic simulation. So the workflow that brings the CFD insights in terms of hydraulics and mechanistic knowledge in terms of chemistry into a simplified version of the same model, which can be run online. So in parallel with the installation, or even faster, faster than the installation, can run quickly very long simulations to test what would be the best action that we take operationally to drive, to steer better the installation. So in the, I forgot something to mention about the slide before. This is the project that you have seen across the whole presentation. This is actually currently the last stage in which we're exploring with the Waterscape Domo the design of their actual digital twins, so that Roberta just mentioned. So in the next slide, instead, you will see, in this case, a drinking water installation in which an advanced oxidation process is taking place. So this is all included in the AMOZONE, right? And the AMOZONE was implemented in this installation, in which the water gets in, it gets treated with ozone plus peroxide, so peroxone process, and then the water follows to the next treatment, which is a UV treatment, in which UV peroxide to the final treatment and removal of the micropollutants. Now, what you see in the graph below is measured data, and the yellow line is the simulated very long time series across years of experimenting with the installation. So that's how the model performed through this data, thanks to the influent information into the influent dynamics, which we could use to run case scenarios or design controllers, just like in this case. So in the yellow lines, you see the actual operation, how the installation was operating in these years. And with the model, we could run advanced controller situations with virtual controllers that would have suggested in this point a better combination of ozone and UV dosing. So balancing the UV power, so saving power because it's more expensive than generating ozone, and limiting the bromate formation. So maximizing the micropollutants removal and at the same time having good quality effluent water with minimal operational costs. Of course, the micropollutants picture is important, and all the micropollutants of interest were monitored in these simulations, making sure, and that's the controller action, the controller's objective, making sure that the target removal, what the utility has to comply with, as the average conversion is maintained. Now, I will take over control of the screen, share my screen, and guide you to a live demo. What you can see here is a drinking water installation in which an influent is flowing through the bubble column 1, and then bubble column 2, and the final bubble column 3. So in this installation, we are now injecting a fixed 1 milligrams per liter dose into the water. You see the controller takes action. We can check the dose from here. So we are at 0.9. So the controller is increasing the dose. And at the same time, the flow is changing. So there is a dynamic flow coming in. So the controller has to adjust in real time the delivered dose, right? So at a certain point, we can have a look at the ozone residuals, how they are. And since it's a drinking water installation, it's very important to minimize bromate and also maintain the required CT. So we see that the CT is fluctuating quite a lot. Then what we can do to reduce bromate is to switch on the other two bubble columns, spread the same dose across multiple points of the across the whole installation, and then continue with dosing. Now the gas flow, it's like switching on the gas flow in bubble column 2 and 3, right? So for a moment we have an overdosing of ozone, and then the controller starts acting on the bubble columns. The gas flow goes down, and then we are aiming for the overall 1 milligrams per liter ozone dose. The ozone residuals decrease again. They go back to normal values, and now the bromate will decrease even further than what it was before, because we are spreading the dose on a bigger volume, and then still the controller will keep on balancing with the influent flow. What happens to the CT is that it still varies because of but is maintained on a reasonable value for this installation for this time of the year. But what we can further do is to change controller and use an advanced one. So making the controller maintain a fixed CT value, for instance, of 1. In that case, that would be the optimal choice, because in the ozone dose will be minimized to maintain the target disinfection rate. And with this, I will give back the line to Wim, because I think we might be short in time at some point. Thank you.
Thank you, Giacomo, for the demo. Always nice to see these demos. Of course, I'm biased. I'm a simulation guy, but always good to see live simulations that are working and operating well. Good. So let's continue a little bit with Q&A. A general question, a very big question is, of course, validation and calibration of a model. So what we can do is group a little bit of questions, because we have had multiple ones, and we can group them a little bit and go a bit further to this slide, for example. So what we have done, of course, throughout the years is checking model accuracy. Yeah? This is very important. Because if you build a mechanistic model, that's what we typically do at AM Team. We build a lot of new models. When we start applying them for the first time, these mechanistic models have to be calibrated and validated. And one of those examples here are a surface water plant and a secondary effluent plant, where you can see, for example, comparisons. We have many of those, but some simple comparisons of measurement data, always in green, versus prediction of the model. So, for example, this is bromate at the left in secondary effluent in a project in the US, Swift. And then we have bromate in a Dutch drinking water treatment plant. And at the right, you can see the target contaminants. And here you can see the different reactivities that are taken into account. So Giacomo, can you maybe elaborate a bit more yourself on how we work now with calibration and validation in these projects?
Yeah, that's a very good point indeed, because the calibration and validation points, it's something we take very seriously, especially when we do an initial assessment for a feasibility study. So as I mentioned quickly at the beginning of the technical part, we take a sample of the water, we make a standardized ozonation test at a dedicated lab, and we calibrate the model on it, and we used other samples to validate the model further. There are other ways to calibrate and validate also with online data. And we often do that when possible, when data are available. Micropollutants data, of course, are not very much available dynamically. Yeah, whatever is available can be used to fine-tune the model. What we have seen is that the advantage of a mechanistic model is that once it's calibrated in certain condition, has a tremendous flexibility across configurations and plant dynamics. That's the main advantage of a mechanistic model.
Perfect. So yeah, calibration in our case means, in this AMOZONE case, means tailoring the model, fine-tuning the model for that plant-specific matrix. And like Giacomo says, once that is done, typically our aim